So, welcome. So, today we're going to continue this, and we're going to start saying, well, okay, if I have a pair of charges, I will get some kind of force, maybe attractive, maybe repulsive, maybe big, maybe small. And I have the equation, and the basic equation is Coulomb's law. And Coulomb's law says that the electrical force is equal to Ke times one of the charges times the other charge. I don't worry about the signs on those over the R squared. R, of course, is a separation. And if I want to make this thing into a vector, now I've got to take into account direction, so I have vector force. And the way I deal with the directional aspect is I multiply this magnitude, magnitudes are always positive, by that force, that unit vector, which is in the right direction. And we did that, we played with it, and you'll notice, look at the diagram to figure out, what you do with the ijk vector. Now, supposing we have a bunch of these things, there's a tendency, I think it's from human nature, to think that if I'm just talking to one person, they have my whole attention, but somehow if I'm talking with two people, I split my attention. And so that must be a kind of universal fact of nature, but it's not, in fact. The interaction between these two charges is never affected by the interaction between those two charges. As far as the one we're interested in, as Q is concerned, now Q has two interactions which combine. But it's not that because F3 occurs that F2 somehow gets diminished or whatever. F2 is F2 because of the interaction between Q and Q2. It never changes. Whilever there's that separation, whilever they've got those values, that's the interaction you get. If I put another charge in there, there's another interaction. It's not that the first interaction is diminished or, The behavior of particle Q might change because now there's several forces acting on it. But each force can be determined and is just invariant even if I add more charges. So basically what I can do is I can say, well, let's just use Coulomb's law on the first charge. Let's use Coulomb's law on the second charge. Let's use Coulomb's law on the third charge. Let's use Coulomb's law on the fourth charge. Let's add them all together. I end up with an answer based on those vector additions. So the way I get the total effect, I'd say, well, the total effect is going to equal to the sum of all the little effects. So we say this Fi, I meaning F1, F2, F3, F4, F5. And so I can write this out a bit more laboriously, and I say, well, there's my sum, and then we put down our equation. So it looks, oh man, this is going on forever. But you remember, equations are just shorthand for what's going on. Now here's the issue. You're adding vectors together, so it's not an arithmetic sum. It's not 3 plus 5 equals 8. It could equal 8 if they're both in the same directions, but it could equal 2 if they're in opposite directions. It could equal something in between if they're at some angle to each other. So we have to do the vector. So each one of these has its own little vector that we've got to figure out. So in principle, you do your calculations, so you get your ijk vector for this guy, and your ijk vector for that guy, and your ijk vector for that. You just add them all together vectorially, get your answer. It looks complicated, but it's actually not so bad at all. The reason why I include this as an example is that it tends to be I noticed when I was teaching AP physics and in my own physics days, and I looked in the textbook, and they tend to like this kind of question. And it's one of those, it's a bit like a joke. It's a bit like the first time you see it, it seems really, wow, what's going on? But once you've seen it, you kind of get it. So I'm not so impressed by them, but I want you to see it. So we have 4 charges. They're all positive. It says 4 equal positive charges laying the points in the diagram. The magnitude of the force experienced by charge X because of charge Y is 3 newtons. There's charge Y, there's charge X. They're all positive. So will this be a attractive force or a repulsive force? It's going to be repulsive because they're all positive. And it says, oh look, that's 3 newtons. Okay, that's nice. Now here's the question. That's all information. Now here's the question. What is the magnitude and direction of the force experienced by charge Z? So actually, I'm not even asking you about charge X as the subject. I just gave that as an example. I'm asking you about charge Z. So looking at this, well, there's going to be a force there, and there's going to be a force caused by the Y, and a force caused by the W, and they're all going to be repulsive forces because they're all positive charges. And then if I look at this, there's some symmetries going on here. This was 2 meters. Well, so is this. So that should be 3 newtons. And so is this between W and Z. So that should be 3 newtons. And actually, so is this one between X and Z. So that should be 3 newtons. The rest of it, frankly, is a bit of vectors. I want to find the magnitude and I want to find the direction. So let's break this into components. So I can put that down. There's one component. There's another component. There's one component. There's another component. And then it's its own component. So there's my 5 components, I suppose you have. And then a bit of trig. If this is an equilateral triangle, then that's 60 degrees, agreed?
Yes, sir.
If this is 60, then this is 60. And if this is 60, then this is 60. Now, you know, shame on me, doesn't that look an awful lot like 45 and 45?
Yes.
And so can you see how I'm struggling a little bit to say which is the 60 and which is the 30? But if I'd drawn it much better, it would be obvious that one of them's 60 and one of them's 30. That's my diagram working against me. That's my diagram confusing it because it's not as good as it needs to be. So it really helps to spend a little bit of time. From my old trig days, I know that this is going to be 3 sine 60 newtons. And this down here is going to be a magnitude of 3 sine 60 newtons. Different direction, but I just care about the magnitudes at the moment. And this here will be 3 cosine 60 newtons. And if that's like, you know, man, where is he getting that from? You've got to go back and you've got to review your components. Remember what we said. If you want something and you got something and you're not using the angle that's between, you're using the complement of the angle, it's a sign of that complement. If I want something and I got something and I'm using the angle in between, it's a cosine of that angle. So however you do it, you've got to get good at that. You had to get good at it for physics 1, you've got to get good at it for physics 2. I say, okay, the sum of the forces vertically is equal to plus 3 sine 60, because it's pointing upwards, added to minus 3 sine 60, because it's pointing downwards, which equals 0 newtons. So those guys just cancel out, yeah? No vertical part to this, agreed? Sum of the forces horizontally is equal to plus 3 cosine 60 added to 3 added to plus 3 cosine 60. Positive because they're all pointing towards the right. And if my memory serves me right in my calculator, then cosine 60 is a half. So that would 1.5 plus 1.5 plus 3 is going to be 6 altogether, yeah?
Yes, sir.
So that's going to be 6 newtons. So it's 6 newtons, and it's pointing to the right. So, like that. So this is kind of it's got some conceptual stuff in about forces caused by charges, but a big part of it is reminding you about the components and the like. It's kind of saying, hey, remember that stuff. You're going to use it, in physics too as well. So I like it, but it's kind of like, I always felt that it was one of those questions where until you'd seen it, you were going, what the hell's going on? But once you've seen it, you go, oh yeah, it's just components. I only have so much time in my tests, so I've got to be a bit more homed in sometimes. That's not to say that wouldn't be a decent question, but it's not my favorite. Okay. I want to talk to you about electric fields. And we've dealt with fields a little bit in the past. We dealt with gravitational fields. But unfortunately, in a way, they're so familiar to us. We take them for granted. I mean, if I told you that you were coming to school to learn about invisible force fields, all your family would be going, ooh, you must be on Star Trek. You go, no, I'm doing about gravity, things falling off a cliff and all that. And you go, oh, well, yeah, we all know about that. So it's unfortunate we're a bit too familiar with it. And to make it even worse, it's not like we go to the top of the mountains and we start kind of floating because it's so weak. And we go to our cellar and we lay it on the floor because it's so strong. It's pretty uniform in our experience. So we tend to think of gravity as being just a constant pull on us. And it is within the range of where we go. And unfortunately, because in Physics 1, you're trying to do so much stuff in Physics 1, we don't have time to go from planet to planet to planet and play that game of, well, what would it be like on Jupiter, what would it be like on Mars? But in Physics 2, we go from charge center to charge center to charge center to charge center. And we're always messing with E. E is the equivalent of little g. We're always playing with the electric field. And so we've got to get used to messing with it in ways that we didn't in General Physics 1. It's a trivial thing, but it's also very deep. There's I can tell you the electric field is the force per unit charge experienced by a charge. That numerically gives its value. But it gets confusing because the electric field is there whether or not I put this force, this little charge in. So the electric field is all about the parent charge. If you like, it's all about the planet. Gravitational field is all about the planet. I have a gravitational field myself, but I'm small compared with the planet. So the way you do these is you look at the effect by looking at my mass in the Earth's gravitational field, and you get the right answer. Or you could look at the Earth's mass in my gravitational field, and you still get the right answer. But the gravitational field is about the object, and you can choose to put another object in there or not. But if you have one object, you have a gravitational field. If you have one charge, you have a gravitational field. You have an electric field, whether or not there's a second charge there or not. We often introduce this idea by having a second charge to see the effects of the electric field. We don't need it, and that can lead to some confusion. So we say the electric field can be considered as an aura. Oh man, don't write that in your graduate essay. That surrounds a charge and is a storehouse of energy. An aura just meaning it's invisible. I suppose auras are not invisible when I think about it, but it's kind of like one of these kind of things where it's an abstraction. The electric field strength, E, at a point in space, so just pick a point in space, is numerically equal to the force that would be experienced by a unit charge. They sometimes call it a test charge that you put on that point. So if I put a 1 coulomb charge there and said to myself, oh, how many newtons am I feeling? And I got the answer of 37.5 newtons, then my electric field would be 37.5 newtons per coulomb, because I put 1 coulomb there. If I put 2 coulombs there, then I suppose I would get 75 newtons. My electric field would be 75 divided by 2 newtons per coulomb, because I had 2 coulombs there. So the electric field is not determined by what charge I put here. It's all about the mother charge. It's all about the big charge. It's about the big charge. It's not that the little charge doesn't have its own electric field, but I'm just not talking about it today. Okay, so numerically you just put a charge there and you say what's the force, and you divide that force by the amount of charge you put there and you got the numerical value. But the important thing to realize is that you don't need to put the charge there. And the way I think about it is, you know, the mountain is there whether you're there or not. You know, the altitude is about the mountain. You've been there, who cares? It's about the mountain. And the electric field is about the mother charge. So, although E is defined, that means defined, is defined as the force over the amount of charge, that should be Q naught, that you put there. You don't have to put the charge there. The electric field strength can have units of newtons per coulomb. We just saw that. Newtons divided by coulomb. That makes sense. It's also volts per meter. Now, let's just justify that for a minute. A volt, we said a volt was a joule per coulomb. It's the amount of energy per charge. So joule per coulomb. And we have a volt divided by a meter And of course a joule, well, that's from work, isn't it? That's a force through a distance. So that's a Newton meter per coulomb divided by meters. Oh, I get it. Newton per coulomb, because that cancels with that. So they're the same thing. A volt per meter is numerically equal to a Newton per coulomb and is dimensionally equal to Newton per coulomb. Different units, but basically measuring the same thing. That's a useful little thing. If we think about our old box, we had force here, and we had electric field here, and we had delta U there, and we had delta V here. We kind of went like that. We kind of linked those two together in a way, yeah? So it's kind of useful for us. By substitution and expansion, we see that separation between the mother charge and the point charge of interest, and the point of interest affects the electric field in inverse square law. So what we're doing here is we're saying, well, we know that Fe is equal to Ke big Q little q over r squared. That's its magnitude. And my electric field equals my Fe divided by the amount of charge I put near the big charge, if I choose to do that. Just define that. Well, if I did that, then what I'd say is that this is Ke big Q over r squared, because I just divided out the little charge. And this really brings home the idea that electric field does not need two charges. It's an inverse square relationship. The electric field falls off just like the force falls off, but you don't need two charges. And these equations, I think, are similar enough to be dangerous. And so that's why you really got to put them side by side. And you really got to recognize, oh yeah, electric force is big charge and little charge. Electric field is only big charge. And they're both inverse square. If I double the separation, I get a quarter the force. If I double the separation between the mother charge and the point of interest, I get a quarter the field. So it's very easy to just gloss over this, and then you end up on a test and you're not sure what equation to use, and you're not really sure what the equation means, and you got no insights. And what we're looking for is insights. Okay. So this is basically saying the same thing. It's going, oh, look, yeah, I can put a unit charge there, but if I divide by the unit charge, then there's the expression for my electric field. It's basically, I wrote it out. What's the magnitude of electric field at a point 3 meters from a 6 Coulomb positive charge? So 6 positive, let's go 3 meters away. So here's my point of interest. And again, it's a pitfall I've learned. I've got to emphasize to myself, it's a point of interest. Because it's very easy at the beginning to just think, oh, it's that other charge. There's no other charge there. There's only one charge here. And yet, we can still sort this thing out. And I can say, well, let's have a look. Fe is equal to Ke, big Q, little q over r squared. And E is defined as being Fe over Q, so that means that it's equal to Keq over r squared. And so I come along here and I go, well, Ke times, well, let's just put numbers in. 9 times 10 to the 9 times Q, good old Q. Q is 6 over r squared, and r squared is, so r is 3, so that's going to be that. Well, that's going to be 6 times 10 to the 9 newtons per coulomb. Now, it's a magnitude, so there's no sign needed for it. It's positive. The only disadvantage with doing it that way is that I'm kind of reinforcing this idea about you have 2 charges and then you cancel a charge out. But you don't need the second charge. You never need the second charge. It's just mathematically that's how you define it. So I can make an argument and say it's actually kind of useful just to learn both equations off the bat, learn them cold, because they're not the same thing. But I can derive one from the other very easily, you know. So you just make your choices about how do you get to the stage where in the test you can figure it out. You could learn that equation, and you could learn that equation, or you can learn how to go from one to the other, you know. Ooh! There's a bunch of them. What do we do? So we basically do the same old. We just you know, sum them. Ooh! Now there's 3 charges, and there's a point of interest. And it says 3 equal positive charges lay at points indicated. The electric field at any point 2 meters away from any individual charge is 6 newtons per coulomb. What is the magnitude and direction of the electric field at point Z? So now, I'm going to put an arrow at point Z caused by X. Should this arrow go towards X, or should it go away from X? Yeah.
Away from X.
Should go away from X. Why? What's your justification for that?
Just like a guess, sir.
Okay, that's not bad. Okay. Anybody got a justification for me? Yes.
Because it's the same kind of thing as the previous parallelogram, right?
Yeah.
The previous one was all pointing away from it, so.
Why was it pointing away from it?
Well, all the charges
Were
exerting their field caused it to exert force.
But what was it about the charges that? When would you get it going towards? When you get the 2 charges attracting?
When they're opposite.
When they're opposite.
They're all the same.
So now we don't have opposite or the same. We only have a positive charge. And so we have a decision to make about our direction of the electric field. And the electric field points in the direction of the force that a positive chest charge would feel. So it points away because that's a positive charge. We had to decide. You have to do one or the other. And so let's just build up a bit of visual kind of analogy. When I think of a positive charge, I think of a volcano. Like Mount Fuji or something like that. I think of something like that. And when I think of electric field, I imagine what a boulder would do on the side of Mount Fuji. Well, the boulder will roll away from the peak. So a boulder rolling down a mountainside is like my electric field pointing away from a positive charge. A boulder rolling into a sinkhole is like my electric field pointing into a negative charge. So if I had a negative charge, it would point towards it. So that analogy that I use it a lot of mountains and sinkholes to look at electrostatic fields because it works quite well actually. So the electric field is going to be there, and the electric field is going to be there, and the electric field is going to be there. And what are they? They are, what did we say, 6 newtons per coulomb, 6 newtons per coulomb, and 6 newtons per coulomb. And the same old, and I'm going to just fly through it. It's like, to some extent, I've done what I wanted to do, which is emphasize the direction. But, you know, you have your component there, and your component there, and your component there, and your component there. And I know that this is going to be 6 sine 60. And I know that this is 6 sine 60, because that is 60 degrees. And I know that this is 6 cosine 60, and that is 6 cosine 60. So I say the sum of the electric fields vertical is equal to 6 sine 60, and that's positive because it's pointing upwards, added to minus 6 sine 60 because that one's pointing downwards, and that equals 0 newtons per coulomb. And I say the sum of my electric fields horizontally is equal to 6 cosine 60 positive, added to 6, added to 6 cosine 60 positive, and that equals 12 newtons per coulomb to the right. So, can you see how, once you've seen that scenario once, it's like the second time is, yeah, come on, let's get on with it.
Yeah, you should put that on the test.
Yeah.
At least explore questions, solve for.
Now, what I could put on the test is I could put on, in fact, let's do one. Now, let's, in the next room there's a little program which enables me to put a slide in. And it didn't get loaded onto when they put these screens in. Somebody didn't load it, and I don't know who's got that program. I can't find it to download. It's driving me crazy. But I'm going to come out of here. I'm going to go, because in the next room I just go, oh, new slide, and it's there. And here it's not. So it's a bit annoying. Now what I can do, which makes this just that little bit more interesting, is I can say, oh yeah, so, so here's a charge. Let's put the charge here. I'm going to say plus 2 coulombs at the origin, and then let's take a point of interest, P. And that is at 6i plus 2j plus 3k meters away. And I want to know the vector electric field. So I go, well, I want to know E. I want to know E. And I say, oh, well, yeah, I know E. E is equal to KEQ over R squared times the unit vector. So E is equal to KE. Q, well, I know Q is plus 2 over R squared. Man. Oh, I know how to do that. Remember we did that before? It's going to be 6 squared plus 2 squared plus 3 squared. And the thing I've always got to remember, got a little alarm bell going. Mustn't forget that square. And then the next thing is, well, hold on, what about its direction? Oh, okay, well, this was the displacement vector. And you know it's pointing in the right direction, isn't it? It's pointing in the same direction as my electric field. So all I have to do is write down that displacement vector and then normalize it, yeah? Normalize it, make it value of 1, divide it by its own magnitude. So E is equal to 2ke over Oh man, trust me, 36 and 4 makes 40. 49? There's my answer. That would be a nice question. It's a bit like I did with the field, with the force question, yeah? And I would say, write me an expression for. Yeah? So what I promised was either one of these two is going to come up, either the force one or this write me the expression for. Boom. There's the skill. This time I didn't give you the two vectors and say work out the thing. This is much more straightforward. I gave you the displacement vector. I said get on with it, you know. So that's not bad. That's doable. But let's make it a bit more interesting. This is physics with calculus. So let's do some calculus. Yes?
One last question. Was the units Newton per meter or Newton per
Coulomb. You know, it's funny when I wrote that, there was a little bit of a little alarm bell went off in my head, and I just put it to one side. But yeah, very well spotted. Good. It's newtons per coulomb. I wish I could say it was a deliberate mistake, but it was a mistake. It's just. Okay, superposition works. You got 10 charges around a point. You'll have 10 electric fields around the point. You add them together, yeah? Let's say there's 1,000,000 charges around a point. Then you have 1,000,000 electric field vectors to add together. And it gets a little bit annoying. I'm an applied physicist, so I came very much out of the physics tradition. And I came through when semiconductors were first coming out, so I remember seeing my first calculator ever. And it was as a junior, and my buddy had it, and it could do multiplication, division, addition, and subtraction. I think it could do percentages as well. And it cost like, I don't know, I mean, a week's salary. It was ridiculous. This guy was the rich kid on campus, and he had this thing. We all looked at it. The first thing we did was we all worked out how you could make it words up by turning it upside down, and you could. So as computers came in, I always tend to underestimate what engineering will achieve in terms of how repeatable it is. I remember buying one of the first laser when I got a Mac computer in the end. I got a laser printer, and I remember the first laser printer I got cost $1,500, and it was awful. It didn't last. Everything I bought for the Mac was $1,500. First scanner, first laser printer. It was on. I bought 1 megabyte of memory. It cost $1,500. It was like amazing. That was I was in industry. I had money, you know, and it was like, and literally people would line up at my desk. I took it to work. People would line up at my desk to use it. It was just so useful. So I got to see, and I got to a stage where I was programming in BASIC on my little Mac computer and, you know, doing stuff. It was like, you know, and really saw the value of being able to use computer programs to iterate answers. And I was working at the time for a company that made electron microscopes, so one of the problems they had was they make the electron beam using a filament just like in a light bulb, but then they've got to confine that into a nice spot, so they put a thimble around it, and then they charge, there's a certain voltage between those two bits, and they get an electric field set up which basically confines the electrons into a really narrow point. And the better you do that, the better your machine. I mean, it's a little piece of metalwork, and if you do it right, you get a better machine than if you don't do it right. So they spend a lot of time trying to make these thimbles just right. And but the way they do it, basically, was they used to paint little pictures, cross-sections, and measure it, like in lab, just like we did in lab the other day. Or they started using computer iteration programs. And computer iteration programs are kind of like, you've got to be a bit careful with them. You can get problems with them. But if you do it right, if you make it fine enough detail, and you let it run, it gets better. And as time's passed, they've got faster and faster, so they've got much better. These things have got so much better. millions of iterations are kind of, you know. So I came to the States with the physics tradition, and I joined material science departments that were in engineering. My first, my first two departments were engineering departments. And one of the people in one of those engineering departments was a guy who became a bit of a mentor. It's always good to have somebody who you kind of admire, who you kind of like. And he was a bit like that. He'd spent time in Europe, so he kind of knew more of my tradition. And one day, he's an engineer, and one day we were talking, and I said, man, it's kind of weird. It's kind of like, I did everything using calculus, and now I can see the value of computers. But when I look at the physics programs, it's mainly calculus with a little bit of using computers. And yet I was looking on this thing, and they seem to do computers for almost everything, and no calculus or not much, And his argument was, you need both. And if you come from my tradition, the best thing I could do was spend more time learning MATLAB and stuff like that. And by the same token, you don't want to be an engineer who can't do a very simple thing because you don't happen to have your computer with you, The stuff you can do by calculus and the symmetries you can see. The trick is symmetries. What physicists tend to do is they look for symmetries all the time. And that makes life, and so as we'll see, it makes life a lot easier when it comes down to doing, even the calculus gets simpler when you do more and more symmetries. So frankly, we cheat with the calculus. We simplify the calculus because we look for symmetries. I'm going to tell you, let me just stop for a second. So if we have a situation where we have a cloud of charge, and who cares what the shape is, but we're going to divide that cloud, which is millions of individual charges, into chunks. And each chunk is going to be a little bit of a cube. And for each one of those, if you think about it, we have a different r, and we have a different unit vector. This guy over here will have a different unit vector, different direction, and a different distance. So that's r2, and that's unit vector 2, and this is r1, and that's unit vector 1. And we've got to sum them all up. It's going to be a total pain. We divide a continuous charge distribution into small elements containing charge, a little bit of charge, delta Q. The electric field due to one of the charge elements is that, we know that, KE, the little bit of charge, delta Q, over r squared times the unit vector, and we summarize them by summing all those little bits. And if we do it finely enough, we can go to the electric field total is equal to the integral of all the little bits of electric field. And we write that out, and we go in integral dE dQ. Now notice, and this is something that when I got introduced to this, I was introduced as y equals what dx by dt or whatever. Integral dx, and it was just the magic symbols. You put one at the front and one at the back, and then you did what you're supposed to do, because we weren't being taught really how it worked. We've just been taught how to do it. But that dx is not just a magic symbol. That q, when you break it into chunks, becomes that dq. And when you break it up into little fine chunks, it becomes that dq. So that dq is a thing. It's not just a magic symbol, it's a thing. It's a physical thing, yeah? So it has meaning from a physics point of view. And so it's important that we're able to do that. So we're going to consider an example. Consider a rod with a uniform charge of 9 coulombs. So CQ, big Q, equals 9 coulombs. The rod lays on the x-axis and extends from +3, so here's +3, to +7, +7. Use calculus to show that the electric field at point P, which is located at +1, so it's +1, so there's my point P, is that. Now in a test, I'd say, what is the electric field at point P? And frankly, in a test, I would say, using the method of calculus as shown in class, because I want to see all these bits. And I'll tell you now, this is going to be the type of question that's on the test. This is one of these things, again, where I'm telling you, this is coming, so get ready for it. I want you to have this skill. So the first thing is we visualize, and then what we do is we try to interpret. So let's go to purple. And, all right, well, what I need to do is I need to write down my expression. And my basic expression is that the electric field is equal to KEQ over R squared. The unit vector I don't need to worry about because it's, you know, I know it's going to be, this is positive charge. It doesn't say, but let's say it's positive charge. So I know my electric field is going to be in that direction anyway. So I don't need to worry about that. I know the direction of my E. So, okay. But now, I'm not going to deal with all of it. I'm going to deal with a little bit of it. So let's visualize. This is my little dq. It actually is something. So I can say, well, in this case, then, my electric field is equal to Ke. It's not Q, it's dq.
Little q?
I'm calling that little q. Yeah. It's just big Q, little q. It's just like, you know, Bill versus William. It's like, you know, the big Q is the total thing. The big Q is the total thing. This little q I just defined as that little q. And it's going to be over R squared. And if I want the total electric field, I've got to integrate that. Just sum them all together, yeah? Okay. I have no idea how to do that. How on earth do you integrate 1 over R squared with respect to dq? It's like, it's not possible. So I need to make a change. And the change I make is, okay, I need to change this into something that has dr in it. You know, the amount of charge I have depends on the width of my little slice. I can integrate that. So I say, well, dq is equal to, I need to do some physics now. So I say it's the little width multiplied by the density of charge. But it's a width, so it's the linear charge density. If I make the little width wider, I get more charge in there. If I make the little width narrow, I get less charge in there. But that's what the amount of charge is. This is physically the amount of charge. It's not a magic symbol, it's the amount of charge. And the amount of charge depends upon how wide my little slice is and what the charge density is on my rod. It's all physics, it means something. So then I say, well, my dq is equal to dr. Now I've got to do something for my linear charge density. It's going to be coulombs per meter. Oh, I have some coulombs up here, so it's going to be Q. But I also need to divide that by a length. And where on my diagram does my rod begin and my rod end? 3 and 7, so that's my length. Yeah, that's my length. Maybe that whole thing is my Q. So I have to have that. Yeah. So now I come along and I substitute this up here. So I say, okay, let's substitute this. And I get E is equal to the integral of Ke over R squared. And then rather than having dq, I put down drq over L. So then E is equal to, let's take out all the constants. That Ke is a constant, and that Q's a constant, and that L's a constant. The R's not. The R's not a constant. The R's the variable. So I have the integral of 1 over R squared dr. Oh, so that equals KEQ over L, the integral of R to the minus 2 dr. KE is equal to KE Q over L, and this is going to be minus 1 over R. Yeah? Is that what that comes out to be? Increase the power by 1, put it in the denominator? Yeah. But I need some limits. On my diagram, where is my R? Can you, I mean, R must be something on my diagram, so where does it begin and where does it end? No. 2 and 6. Well, no. Where does R begin? Look back at your diagram. Where did the R begin? On here. Begins on the little square, doesn't it? And it points towards the point of interest. So where does R begin for this little purple bit? It begins on the purple bit and it points towards the P. So what's the longest that R can be? Think about the beginning and the end. It goes from the 7 to the 6. There's my R in this case. Yeah? There's my R in this case. Well, the longest that this could be is over here. And that would be an R of 6. Because it goes from the 1, well, from the 7 to the 1. So the longest this could be is 6. What's the shortest that this R separation could be? 2. Okay? So you see I get those limits. And again, it's pointing back to the physics of the situation. So then I say, well, E is equal to KE. Let's put some numbers in. 9 over. My L is going to be 7 minus 3, which is 4. Times minus 1 over 6 minus 1 over 2, which equals, let's do it, 9 over 4 KE, and this is going to be minus 1 over 6 plus 3 over 6, which equals 9 over 4 KE, and that's going to be 2 over 6. So E is going to be 0.18 over, whoa, something, I did something wrong there. 9 over 4, 9 over 4, 9 over 4. Oh no, that didn't right. No, 9 2s are 18, 4 6s are 24. 18 over 24, which is 0.75 KE newtons per coulomb. So can you see? It's calculus, but it's physics-based calculus, if you like. You know, it's like, it's really important to me that you can justify those steps. It's not. I know that you can do the integration. I hope you can do the power integrate. You know, I hope you can do the integration. It's not about that, is it? It's about how do you go from dq to dr. That's what I want to see. So on the test, I'll say using the method of calculus as shown in class, and it'll be a question like that. And I'm going to want to see that you know the original equation. I'm going to want to see that you can justify making the change. I'm going to want to see that you know your limits. So if you jump in, you know, if you learn, I'm just going to learn, you know, the answer, no points. It's going to say using the method of calculus as shown in class. So I want you to have those skills. And then the next time we do one of these things, more of the skills will be there. Okay? It will only be on a line. I will not put it over to the side because that's a much harder calculus problem. I might put it here. I might put it here. I might put it here. I might put it in the negative terrain. Who cares the address? It's on that line. I might make the whole thing vertically just so y versus x. But the whole thing will be vertical rather than horizontal. The same basic problem. Okay? So watch out for that. Cool. Questions? Cool. In this next bit, to be honest, when we had cathode ray tubes like TV tubes, this was really kind of important. We had this situation where we could make a force on a charge using electrostatics, rather like force on a boulder using gravity. And so we could mimic what happens with gravity with electrostatics, which say the force is equal to the electric charge, which for an electron is E times electric field, and F equals ma, and we put them together and we can find a term for the acceleration felt by an electron, and then we could shove it into this thing and play with it. And frankly, I don't care about it so much these days. So know that it's there, but I'm not going to ask you a question on that, okay? Okay? So let's stop there.